I'm finally sitting down to complete the work that I've been planning for a while. Yes, what is it? I can surely say my equilibrium is disturbed right now by all these factors around me. As much as I would like to concentrate, external factors keep disturbing me. What happens to chemical equilibrium when subjected to various disturbances? Join me in the studio and I will answer that. Hello and welcome to our episode on Chatellier's principle. Have you ever thought that the human body appears stable even when it's actually undergoing thousands of chemical reactions every second? What helps it maintain this stability? It's called equilibrium, which is central point of our learning today. In this episode, we will study equilibrium constant and its significance, derive the relation between equilibrium constant Kp and Kc, and relation between Kc and reaction coefficient Qc. Understand Chatellier's principle and factors affecting equilibrium. And finally, in Exam Decoded, we will take a look at how to tackle exam questions. You know that in any chemical process, equilibrium is achieved only when the chemical activities or concentrations of the reactants and products have no net change over time. The concept of chemical equilibrium became more established after the French chemist Berthollet discovered that some chemical reactions are reversible. The reversible reaction really involves two reactions. There is a forward reaction and a reverse reaction. In a forward reaction, reactants react to form products. In a reverse reaction, products react to produce the original reactants. Now, you must note that reversible reactions reach equilibrium when the rate of forward reaction is equal to the rate of backward reaction. Isn't it interesting that while iron takes a few days to get oxidized, that is form rust, millions of chemical reactions occur within a second in our bodies? The rate at which a chemical reaction proceeds is clearly a unique variable. To know the rate of reaction, Norwegian chemists Cato Gullberg and Peter Waj postulated the law of mass action, which states that the rate of reaction is proportional to the product of the active masses of the reacting species involved in the reaction raised to the power of the stoichiometric coefficients as given in a balanced chemical equation. In this, active mass refers to the number of moles of the substance which are present in unit volume and is represented by enclosing the formula of the substance in square brackets. If we apply this law of mass action to a reaction shown at equilibrium where capital A and B are reactants, capital C and D are products, small a, b, c and d are the stoichiometric coefficients of capital A, B, C and D respectively, the rate of forward reaction will be proportional to the product of active mass of A raised to the power small a and active mass of B raised to the power small b. The rate of reverse reaction will be proportional to the product of active mass of C raised to the power small c and active mass of D raised to the power small d. To remove the proportionality sign, we will need to introduce a constant K1 for forward reaction and K2 for reverse reaction as shown. At equilibrium, the rate of forward reaction is equal to the rate of backward reaction. On equating the two equations, we will get equation 1, and as K1 and K2 are constants, we can replace them with a constant capital K called equilibrium constant. When the concentrations of the reactants and products are expressed in moles per liter unit, the equilibrium constant K is written as Kc. Now, let us try and understand what is the significance of equilibrium constant. You see, when the value of equilibrium constant K is very high, the reaction proceeds to almost completion. If the value of K is greater than 1 but not too large, the reaction in the forward direction is favored more than the backward direction, and vice versa. If the value of K is equal to 1, both the forward and backward reaction are almost equally favored, that is, a state of equilibrium is reached. Now, if the reaction is a homogeneous gas phase reaction, then the molar concentration of a substance is directly proportional to its partial pressure P at constant temperature. In this case, the equilibrium constant is expressed in terms of partial pressure of the reactants and products, and the equilibrium constant K is denoted by Kp. To relate Kc and Kp, we will use ideal gas equation and relate pressure to concentration by Pv is equal to nRT. Now, you are aware that concentration is given by the ratio of number of moles per unit volume. Using this, we can express pressure in terms of concentration. On the basis of this formula, we can express equation 1 in terms of concentration as well. Now, delta N is equal to the change in the number of moles of the gaseous components in going from reactants to the products. So, Kc and Kp can be related as shown by equation 6. Time for me to ask you a question. Can you name at least one natural process in the human body which can be understood with the help of equilibrium constants? Before I answer that question, I will take a short break while you try figuring out the correct answer. And when I return, there will be lots more on equilibrium and factors affecting it. So stay tuned. Welcome back to our episode on Chatellier's principle. Here is the question I had left you with before the break. Can you name at least one natural process in the human body which can be understood with the help of equilibrium constants? The answer is equilibrium constants help understand the transportation of oxygen by hemoglobin in blood in the human body. And do you know why? For that part of the answer and more, log on to www.topperlearning.com. Now, what if the equilibrium constant does not involve equilibrium concentrations? This brings us to a new term called reaction quotient, denoted by Q. Qc with molar concentration and Qp with partial pressure. Though Q has the same expression as the equilibrium constant, it denotes concentrations at points in a reaction other than at equilibrium. If the concentration becomes equal to equilibrium concentration, then reaction quotient Qc equals to equilibrium constant and Kc is equal to Qc. On comparing the equilibrium constant and quotient of a reaction, that is Kc and Qc, if Qc is greater than Kc, the reaction will proceed in reverse direction, producing more reactants. If Qc is less than Kc, the reaction will proceed in forward direction, producing more products. Now suppose you have equilibrium established between substances. What would happen to it if you manipulated the conditions and the amount of the reactants? Henry Louis Le Chatelier and Carl Ferdinand Braun gave the world the answer to this by providing a single principle which is used to predict the effect of a change in conditions on a chemical equilibrium. This is the Le-Chatelier's principle, also called the Le-Chatelier-Brown principle, which states that if a chemical system at equilibrium experiences a change in concentration, temperature, volume, or total pressure, then the equilibrium shifts to partially counteract the imposed change. So what are the various factors that affect equilibrium? Let's discuss some of them. The first is concentration. Changing the concentration of either a reactant or a product will shift the equilibrium to the side that would reduce that change in concentration. And an experiment in the laboratory is the best way to observe this postulate firsthand. Take a test tube of 0.1 molar solution of ferric nitrate. Add a drop of potassium thiocyanate to it. The intensity of the color becomes constant on attaining equilibrium. It gradually grows red to attain a deep red hue that doesn't change. Now this equilibrium can be shifted to the opposite direction by decreasing the concentration of Fe3 ion by adding oxalic acid. Oxalic acid reacts with the Fe3 ion and forms iron oxalate, thereby decreasing the concentration of Fe3 ion. This is determined by the decrease in the intensity of the red color. By Le-Chatelier's principle, in order to minimize the effect of change in decrease in concentration of Fe3+, the red colored complex dissociates to shift the equilibrium. We can now conclude that a decrease in concentration of a reactant will shift the equilibrium in the backward direction. Similarly, an increase in the concentration of a reactant will shift the equilibrium in the forward direction. Similarly, equilibrium can also be manipulated by varying the amount of the products. Next, let us look at the impact of changes in temperature on equilibrium. When the temperature of a system at equilibrium is increased or heat is supplied to the system always moves in that direction in which the added heat is absorbed. That is, its effect is nullified. So, an increase in temperature of a chemical system at equilibrium favors the reaction that proceeds with the absorption of heat. That is, it should be an endothermic reaction because in endothermic reactions, heat energy is absorbed. Let us look at an experiment to verify this. In the equilibrium established when cobalt-2 chloride is dissolved in hydrochloric acid, the equilibrium is between a pink and blue complex of cobalt and has purple color. Here, the forward reaction is endothermic and backward reaction is exothermic. Therefore, in hot water, the forward reaction is favored, and so the solution is blue. At 0 degrees Celsius, the reverse reaction is favored, so the solution is pink. Fascinating, isn't it? At this point, I'd like to take a pause and address a query from a student. Let's hear it.
Can I know if increase in temperature also affects equilibrium in exothermic reactions?
Yes, it does. Increase in temperature will shift the equilibrium in the backward direction, which is the reactant side. Now, in most cases, it is far more viable to shift reactions to the product side. In an exothermic reaction, this can be done by shifting the equilibrium forward, which would require lowering of the temperature. One of the most important applications is the production of ammonia, which is an exothermic process. In industrial production, companies aim at producing as much ammonia for as little cost as possible. Therefore, the reactions generally happen at higher temperatures. However, since this favors a reverse reaction as well, a compromise of about 450 degrees Celsius is used. Next, let's discuss the effect of change of pressure on equilibrium. On increasing pressure, the position of equilibrium will move in such a way as to decrease the pressure again. This can be done by favoring the reaction which produces fewer molecules. And if there are same number of molecules on each side of the equation, then a change of pressure makes no difference to the position of equilibrium. In a gaseous reaction, where there is a change in the number of moles in going from reactants to products or vice versa, pressure plays an important role. When the pressure on a reaction involving gases is changed, the equilibrium will shift in a direction so as to undo the effect of change in pressure. Let us relook at the equilibrium for formation of ammonia from hydrogen and nitrogen. As the increase in pressure decreases volume, the equilibrium shifts towards lesser number of moles. That results in decrease in volume. Thus, formation of ammonia is favored by increase in pressure. If the pressure is decreased, the volume increases. So, the reaction where the number of moles increases will be favored. In this case, it will be the reverse reaction in which ammonia will get dissociated. Don't you think the Le-Chatelier principle reflects my condition at the beginning of the show? I was trying to concentrate hard on my work when I got repeatedly disturbed, very similar to the changes that affect equilibrium. And like chemical equilibrium shifts to neutralize those changes, I continued my work regardless of the disturbances. And that brings us to the end of this segment. But don't go anywhere, because we have exam decoded in just a short while with all the information you'd want on exam questions, as well as expert advice and tips on how to perform your best, coming up after the break. Welcome back to our episode on Le-Chatelier's principle. Let's take a look at what we have discussed so far. We have studied the definition of equilibrium constant as the relationship among concentration of reactants and products at equilibrium. Le-Chatelier's principle states, if a change is imposed on a system in equilibrium, the position of the equilibrium will shift in a direction that tends to reduce that change. Increase in concentration of reactants or decrease in concentration of products will favor equilibrium in forward direction and vice versa. At equilibrium, increase in temperature will favor endothermic reactions and decrease in temperature will favor exothermic reactions. Increase in pressure will favor the reaction wherein the lesser number of molecules are formed. With this quick summary, let us crack some questions in Exam Decoded. Welcome to Exam Decoded. If you have been listening to me closely, then you will be prepared for what's coming up next. So bring out your best ammunition, because this is rapid fire time. I'm going to ask you 5 questions with 5 seconds to answer each one. The questions will either be multiple choice or you will have to decide whether the statement is true or false. Each correct answer will fetch you 1 mark. So are you ready to begin? Your first question is, at equilibrium, A, Q is greater than K, B, Q is equal to K, C, Q is less than K, D, Q is equal to K is equal to 1. The answer is B, Q is equal to K. That was not tough. Here comes the next question. The reaction proceeds in forward direction when A, QC is less than Kc, B, QC is greater than Kc, C, QC is equal to Kc, D, QC is equal to 1.5. And the answer is A, QC is less than Kc. Okay, on to the third question. The equilibrium constant for a gaseous reaction is denoted by A, K, B, Kc, C, Kp, D, Q. And the answer is C, Kp. Now the fourth question is, increasing the temperature favors an exothermic reaction. Is it true or false? And the answer is false. Hope you got that one right. It's time now for the fifth and the last question of this round. If the concentration of reactants and products are doubled, then equilibrium constant K will be unchanged. Is it true or false? And the answer is true. If the concentration of reactants and products are doubled, then equilibrium constant K will be unchanged. So how did you fare? You must be feeling on top of the world if you got all 5 right. Congratulations, you are our topper high flyer. If you almost got there with 3 to 4 right answers, you are the achiever on today's episode on Le Chatelier's principle. Keep your focus, and that odd 1 or 2 mistake too can easily get straightened out. If you have scored less than 3, you are a learner. This means you need to log on to our website www.topperlearning.com and make good use of all your practice tests. The topic Le Chatelier's principle belongs to the unit equilibrium that carries 6 marks in your exams, and so it ranks as critical on our weightage meter. Questions asked from this topic are usually very short answer type for 1 mark and short answer type for 2 to 3 marks, and are largely knowledge ability questions that will test your recall of key variables and their interrelationships. Here is an example of another 2-mark question and also the correct way to answer it to score full marks for your efforts. The question is, in an equilibrium of carbon monoxide and hydrogen gas reacting to form methanol, give the effect of increase in pressure. CO plus 2H2 gives rise to CH3OH. This is a question of average difficulty and is worth 2 marks, as I mentioned earlier. Let us now take a look at how to answer it. You should start with this explanation. As per Le Chatelier's principle, increase in pressure will favor decrease in volume, and the reaction will shift to the side with the fewer number of moles of gas. You will get 1 mark here. Next, you should write, in this case, formation of CH3OH, the forward reaction will be favored as the forward reaction has fewer molecules. You will get 1 more mark for this. It's time now to go over to our exam expert, whose tips will help you get that extra edge to your scores.
Student, the topic Le Chatelier's principle is very important. If a system is in equilibrium and is subjected to change in concentration, pressure, temperature, then equilibrium has unto the effect change imposed on it. Effect of concentration. If we increase the concentration of reactant, then equilibrium will shift in the forward direction. If we increase the concentration of product, then equilibrium will shift in the backward direction. Effect of temperature. If we increase the temperature, then endothermic reaction will be favored out. If we decrease the temperature, then exothermic reaction will be favored out.
I am sure these tips have given you enough ammunition to tackle your exams. A final input from me is, if you are getting too distracted while you study, remember the Le Chatelier principle. You will have to move to a state which neutralizes those distractions so that you stay in equilibrium all the time. Follow that and nothing shall stop you from topping. As always, keep thinking. See you next time.